Welcome to my podcast on logistic growth and partial fractions. One of the logistic growth problems that you'll see a lot looks like this. In which P and T are your variables and K is a growth constant and M, as you remember, is your carrying capacity or the maximum that an organism can reach population-wise in an environment. And what I want to do really is show you how you get to the general solution for this problem and recommend to you that you really just memorize the general solution. And this is not a derivation for the faint of heart, but sometimes it helps to sort of understand where the solution comes from. So in order to get to this solution, we're going to have to do our separation of variables process. And so you can see at this point, now that I've separated the variables, I'm ready to do it's a pretty ugly integration sign. Sorry. But let me erase that and kind of clean this up a little bit to make it look a little bit prettier. So I've got K dt. Okay, now the left side is really the problem for us because that's our integral that we're going to have to do by utilizing partial fractions. So let me work that out for you. So the actual fraction part without the differential is clearly, or rather the denominator of the fraction is clearly factorable into its two factors. You can already see there. And so at this point, we go ahead and go through the process again. Go ahead and let P equal M. And so we'll get that 1 is equal to A times 0 plus B times M, which tells us that B must be equal to 1 over M. Repeat the process again. This time we make P equal to 0. We make P equal to 0, we get 1 equals A times M plus B times 0. And that clearly means that A is also equal to 1 over M. So as you can see, we now have been able to break up exactly what we've got. So let me go ahead and erase this part, make this a little bit cleaner. So let's see exactly what we've got here. So our left side integral, dp over P times M minus P, is going to really be 1 over M times 1 over P dp plus 1 over M times 1 over M minus P dp. So doing this integral now, I'm going to get 1 over M times the natural log. I think what I'll do is I'll just go ahead and close everything in. The natural log of P, absolute value. But P is probably always going to be positive since we're talking about population. So those absolute value bars are actually unnecessary. So I'm going to take those out because it kind of makes it a little neater if I just leave it. Now, watch out here, because when you take the antiderivative of 1 over M minus P, you get an extra minus out there because of the chain rule. See how many of you picked up on that, understand exactly why I'm doing that. So that's what we've got for that integral. And of course, we pay attention, we know that k dt is simply kt plus c. All right, so we've got our integral done, but now you can see we've just got a lot of manipulation to do. And so that's what I'm going to really spend the rest of this process doing, is taking you through the complete manipulation. So I'm just going to clear the board. And just recopy some of this. And really, the rest of this is just the process of making this look like the actual solution to the problem that we want. All right, so I think this is going to go pretty quick from this point on. So I'm going to go ahead and recopy what we've got. So we've got natural log of p minus natural log of m minus p. And I'm going to multiply both sides by m, so we're going to get mkt plus, now when I multiply m times c, I just create a new constant, so I'm just going to call that constant c sub 1. All right, so I'm going to go ahead and get rid of this now. And now we'll just go through the whole process. Now, the next step I'm going to do is I'm going to multiply both sides by -1. So what that's going to do is that's actually going to change the direction of the subtraction. And so I'm going to go ahead and write that now as a fraction. And then over here, obviously, this is negative mkt minus c sub 1, because we multiplied everything by -1. And then, of course, I do the great trick, which I always use to get rid of natural log, and that is making both sides into a power of e. So what that lets us right now is that m minus p over p is equal to e to the negative mkt minus c sub 1. Those of you who have been paying attention to past podcasts know that what I'm going to do is I'm going to take that negative c sub 1 and I'm going to make it its own separate power of e. So with a little more sneaky manipulation, the left side is really just m over p minus 1, isn't it? On this side now, I'm going to create a brand new constant, which I could call c sub 2, but I think what I'm going to do is I'm going to give it just a completely different letter. I'm going to call it a. And so this would be a times e to the negative mkt. So we're pretty close to our final answer here. So we've got m over p equals 1 plus a times e to the negative mkt. We'll put that in parentheses. And then just doing a little bit of using means extremes property, I can pretty much finish the problem off by writing that p is equal to m divided by 1 plus a times e to the negative mk times t. And that gives us our final solution to the logistic growth problem.